Hey class, so last week when we asked about what topics we were having the most trouble with, a vast majority of you said that you were really struggling with calorimetry, particularly how to set up the problems and the signs that you use, and also how the algebra works. So I'm going to go through a brief overview of calorimetry, sort of explaining it in more detail, and then we'll do an example problem where I can try to demonstrate some of the best practices to use when solving a calorimetry problem. So to start off with, remember Q means heat. Okay, so the key, and more importantly, it's heat exchange, because remember, if heat's going into the system, it's positive. And if heat's coming out, it's negative. Okay, and the system is really just defined by you. So when we're talking about a particular system, in the case of calorimetry, that can be ice, or it can be steam, or it can be water, or it can be mercury. It can be any of the materials. And usually we're talking about putting two systems. So calorimetry is putting two or more systems. That means like ice and water, or ice and steam, or mercury and water, or iron and ice, okay? All of these, two or more systems in thermal contact, okay? And thermal contact just means touching, okay? So if you put ice in a cup of water, now you've put ice and water, two different systems in thermal contact. So every time you fill up a glass with ice water, now you have thermal contact. You could also include the glass, and then of course it's open to the outside environment, so that's a little bit tricky. If you really want to create an isolated two systems, then you'd have to put ice water in a thermos, okay? Anything that prevents heat exchange with the outside environment. So essentially we're putting things in thermoses, but overall we're just putting systems in thermal contact. So if you do calorimetry in a lab, you'll use some sort of insulator like a thermos. The other thing to keep in mind is, so for calorimetry, that means if you add up all your heats, right? So sum of all heats equals 0. So if you sum up all heats. But what this means in practice is, like, if you have Q1 plus Q2 plus Q3 plus Qn, you get 0. So if you're dealing with ice melting, that means you need 1 Q for ice to go through a phase change and 1 Q for ice to change temperature, because we have two different types of heat that we can deal with. So we have the classic MC delta T. This is for any temperature change. And you notice this is within one state, so within the same phase. So in a liquid, in a solid, or in a gas. And then you have this other Q, which is plus or minus ML, where L is the latent heat. And this is for phase change. And so then you really just have to use these two equations, and you plug them into this equation. And the only thing you still need to know is that once you put these things in thermal contact, they eventually reach equilibrium. Where everything's at the same temperature. Equilibrium just means it's been sitting around a long time and now everything has sort of reached the same temperature. It's true of, so basically if you're in a room, and we talked about this a little bit in lecture, everything is room temperature unless it generates its own heat. So you're not room temperature because you're a mammal, so you don't generate your own heat. You do generate your own heat, right? So you're converting chemical energy from eating food into heating your body so you don't die. That's a whole thing. But if you're a table or a chair or an ice cube, eventually you're going to reach the same temperature as the rest of the room because the room is much bigger than you. So heat is transferred to do that, and it keeps transferring until it does that. So we end up with this as our condition for calorimetry. So we're summing up all the heats The two kinds of heats are these heats, and then we also need to know that we're always dealing with thermal equilibrium, okay? Now, this is all fine and good, but the tricky thing is picking when you use each heat and then also how you apply this in a problem. So we're gonna do an example problem. Okay, so let's do an example problem that you can find in the book. This is 17.37 in the textbook, or the 14th edition of the textbook. So we have a blacksmith who cools a 1.2 kilogram chunk of iron. It has an initial temperature. It goes down to 120 Celsius. And we want to know, this water is 15 degrees and it all boils off into steam. So we want to know how much water does the blacksmith trickle over the iron. So let's start by sort of drawing a picture and figuring out what we know. So let's say this is our iron. It starts out pretty hot. So we have iron. It has a temperature of 650 degrees Celsius. And we'll call that temperature initial of iron. It has a mass of 1.20 kilograms, and that's all we really need to know. And we'll draw a little, it's hot right now. So that's how we know. We also have water. So your blacksmith's gonna trickle some water over this iron. And the water has a temperature initial of water of 15 degrees Celsius. We don't know the mass of the water, but we do know that all of the water turns into steam. So at some later time, let's say we have all the water has now turned into steam. And we'll call this, we know the temperature of the steam is going to be 100 degrees Celsius. We know the mass of the steam should be equal to the mass of the water because all of the water becomes steam. So if this is what's happening. We have this plus this becomes steam plus now cooler iron. So now our iron, has a temperature iron final of 120 degrees Celsius, has the same mass, and that gives us a change in temperature for iron and a change in temperature and phase for water. Because remember, when we're talking about calorimetry, we want to sum up all our Q's and they equal 0. What that means is, in this case, Q for iron plus Q's for water, which is both, this is going to give us 2 Q's because this is going to be change in T and then phase. This equals 0. In English, what that means is all heat leaves iron and goes to heat water and make steam. So when we talk about our Q for iron, remember we have 2 different kinds of Q's. We have Q MC delta T, that's just for temperature change, and we have Q equals ML, and that's for phase change. So temperature and phase, okay? we're just going to use the temperature one for iron because it's not melting or boiling, so it's going to stay the same phase. We don't have a phase change for iron. So that's going to be mass of iron plus C for iron plus delta T for iron, okay? And we know that this Q needs to be negative. And why does it need to be negative? Well, it needs to be negative because this is a minus Q. Because it's going to give us, because the heat is leaving the iron. So that means all of the Q's must be negative. You don't actually have to put that in because it's going to show up in the temperature difference, okay? Our final temperature is 120. Our initial temperature is 650. So you're going to subtract those, and that's going to give you a negative 530, okay? So we're not going to worry about that just yet, but that's our Q for iron. Our Q for water is actually Q for water and Q for water to steam. Okay, so the Q for water is this just the mass of water, right? The specific heat of water and the change in temperature of water from 15 degrees to 100 degrees. So final is 100 minus 15. Now that should be positive, okay, because heat's going into the water, and it'll be shown in this part because when you look at this part, you're gonna do final minus initial, which is 100 minus 15, so that's gonna be 85 degrees, all right? And remember, you don't have to convert from Kelvin and Celsius when you're subtracting because they have the same increments. 1 degree Kelvin is equal to 1 degree Celsius, not on the absolute. So we're going to leave things in Celsius. The other thing we want is this change. So we have a phase change where we go from water into steam, and all of the water becomes steam. It says all of the water boils away, so that we know the mass is the same. The mass of steam is the same as mass water, and then we need to use the latent heat of vaporization. And the only tricky thing here is the sign, but remember, we're putting heat in to make water go from water to steam. So from a liquid to a gas, that takes heat. So this is also going to be plus, okay? So basically this is negative and these are positive, and they should add up to 0 because all of the heat that comes out of the iron is going to end up in the water and steam situation, okay? So we set all this up, and that means that we end up with, so mass of iron, C iron, delta T iron is equal to, this is Q iron plus Q water, which is mass of water, C of water, delta T water, which this is Q water. And then we get mass of water, latent heat of vaporization for water. And this should all equal 0. So this is Q steam, okay? Remember, this should be minus, plus, just to check. And then we can plug these in and solve, because the thing we want to find is actually mass of water, because that's the only thing we don't know, and it's what we're asking for. So when we do the algebra, we just solve this for mass of water, which means that we can group things nicely. So we end up with some algebra here where we have this is equal to mass of water. Should be negative here, just from the algebra. And then we have C water, delta T water, plus latent heat of vaporization of water. So that gives us mass of water is equal to negative MICI delta TI divided by C water delta T water plus latent heat of vaporization of water. Okay. All right, so I'm just gonna make some stuff a little bit smaller. All right, we can plug in our actual values. A couple other things you wanna remember, we can look these up, but the specific heat of iron is going to be 0.47 times 10 to the third joules per kilogram Kelvin. The specific heat of water is going to be 4.19 times 10 to the third joules per kilogram Kelvin. And then the latent heat of vaporization for water is going to be 2,256 times 10 to the third joules per kilogram. So we can plug these things in. This is going to give us negative mass of the water, so that's 1.2 kilograms, 0.47 times 10 to the third joules per kilogram Kelvin. We also have delta T, so that's going to be 120 degrees minus 650 degrees. Remember, this should give us a negative value, as we talked about before. Okay, in the denominator, we have the 4.19 times 10 to the third joules per kilogram Kelvin. That's the specific heat of water. The change in temperature should be 100 degrees C minus 15 degrees C. And then we're adding this 2256 times 10 to the third joule per Kelvin. Okay. When you plug all this stuff in and put it in your calculator, you get 0.114 kilograms. Now this is the mass of water that you have to use in order to cool down your iron. So 0.114 kilograms. Okay, this is a very small amount of water, which causes a very large temperature change in the iron. And that's because the high heat of vaporization, so it takes a lot of energy to turn liquid water into steam. And the specific heat of water is actually also very high. And then we have a very low specific heat capacity of iron. So iron loses heat really easily. Water can absorb a lot of heat pretty quickly. And that's how we end up like this. But the key thing here is getting the signs correct, and making sure that your answer makes sense at the end. The rest is mostly algebra. But it's always good to draw out what we did up here, draw out which things are happening, and write out what's going on. So remember, all the heat's leaving the iron and going to the water. If heat's leaving, that means your Q's should be negative. So whether you get that by choosing a negative sign in the case of phase change, or by getting it from a temperature change by being careful about what's initial and final temperature, it's good to know if your heat should be positive or negative.